All right, we're going to look at this population model problem that we have here. And so we're given a differential equation that describes the growth of this population, but then we're given some other information that they're going to change the way the population grows by adding in this harvesting. So we want to modify the differential equation to account for that and then analyze what's going to happen with that situation. Before we modify the differential equation, though, I just want to talk a little bit about what this population is doing before the harvesting starts. And so if we look at the differential equation that we're given, we can think about that. We've analyzed some like this. You can see that there are two equilibrium solutions, 0 and 1,000 are equilibrium solutions. If you set the differential equation equal to 0 and solve for p, you get these two constant solutions. And so those are two equilibrium solutions. And you can make a phase plane portrait here. We've done this with some other differential equations before. The 1,000 is a stable equilibrium solution, and the 0 is an unstable. Of course, populations below 0 maybe don't really make sense there. But we have a stable equilibrium solution at 1,000. That's 1,000 individuals, so really 1,000,000 individuals in the population. But because that's a stable equilibrium solution, eventually the population is going to approach that level and level out so that we have this stable equilibrium solution here. All right, so what we want to do now, though, is modify the differential equation so that we can account for this harvesting and then see what's going to happen to the population. So it'll no longer behave exactly like this, but see what's going to happen to the population when we have that harvesting incorporated into our model here. All right, so we've got the population being modeled by this. And then we know that they're going to harvest or take out of the population a fixed number of individuals per month. So I'm going to use H to designate that fixed number of individuals per month, and that's going to decrease this population. So we'll just have a minus H there. So that's going to be that harvesting level. In number of individuals, thousands of individuals per month. All right, so here's our new differential equation, and what we want to do is analyze that and think about what are the new equilibrium solutions for this. So this is a little bit complicated to think about because this H here is a constant, a fixed, tells us that we're going to remove a fixed number of individuals per month, but we don't know what that is. It could vary depending on what level the wildlife manager decides to establish the harvesting at. So we've got this parameter here, a constant, but it could take on different values. All right, so we want to think about the equilibrium solutions of this new differential equation. So we're going to set that equal to 0. And I'm going to go ahead and distribute through and do a little simplifying as I do that. I'll have a p squared term here. And if I just simplify the coefficients, 0.04 times 1 over 1,000, we'll get a negative 0.00004 p squared, and then we'll have a p term, and then our h term, which remember is a constant, but it's a constant that we don't know what that is. And so we want to solve this for p to find our equilibrium solutions. Our solution will involve h because that's our unknown constant here. So we probably want to multiply through by -1 and then maybe use quadratic formula to solve this. So when I do that, I'm going to just go ahead and multiply through by -1 to make the coefficients a little nicer in my quadratic formula. Remember that this is not the differential equation, but because I've set it equal to 0, I can multiply both sides of the equation through by -1. I don't change the equilibrium solutions. And then I'll use quadratic formula. So negative b, so positive 0.04, plus or minus the square root of b squared, minus 4 times a times c. All over 2a. All right, so we've got kind of a big mess here, but this does simplify very nicely. So I'm going to go ahead and write down the simplified version here. When you simplify that, the 0.04 divided by 2 times 0.00004, we'll get 500 plus or minus. And then you've got some common factors here, perfect squares that you can factor out and simplify with this denominator as well. We get 500 times the square root of 1 minus h over 10, or 0.1h, depending on how you want to simplify that. All right, so there's a lot of ways you could simplify this, but the key thing here is that you want to think about how the different values of h change the nature of these equilibrium solutions. So I've got a quadratic equation here. You know that in general you have two solutions to a quadratic equation, except in the case where they're both the same solution, a repeated zero, or when the expression under the radical is negative, you have non-real solutions which don't really have any meaning in the context of a population. And so in sort of thinking about how the different levels of h impact what's happening with this population that's described in this word problem, we really see here that this expression under the radical, when this is 0, that's going to change the behavior when this is 0, or when this is positive, or when this is negative. And so that's what we have talked about before. You've got this value for the parameter, which changes the nature of the solution. So that's a bifurcation value. And so this expression under the radical will be 0 when h is 10. Remember that that's in thousands of individuals per month. So that would be 10,000 individuals per month harvested. I have a bifurcation value when h equals 10. When h equals 10, this expression inside the radical is 0, so this whole term is 0. So I really just have one equilibrium solution in that case. So when I harvest 10,000 individuals per month, I get one equilibrium solution at p equals 500,000 individuals. And if you draw a phase diagram, phase plane portrait for that 500 equilibrium solution, so you'd be looking at the signs on this differential equation. We're going to go back to the original differential equation, not after we multiplied through by a negative here. You're going to have a repeated 0, and this differential equation will be negative everywhere, and so we've got decreasing population curves everywhere. So your population curves would look like that. So this is a semi-stable equilibrium solution. And basically, your population, if it starts out here at that stable equilibrium solution before the harvesting at around 1,000, and you start harvesting 10,000 individuals per month, then that population is going to drop down and stabilize at around 500. I'm going to be careful about that, though, because what this shows is that if that population drops below 500, though, that population is going to crash, and the population will eventually go to 0. So we have this bifurcation value at h equals 10, and then I have two other cases to consider, really. What happens when h is bigger than 10? What happens when h is less than 10? I'm going to look at h less than 10 first of all. All right, so when h is less than 10, this expression inside the radical here will be positive. Right? When h is less than 10, this expression inside the radical will be positive. So you'll have two distinct real solutions. You'll have two equilibrium solutions. One of them will be at 500 plus 500 times the square root of 1 minus h over 10. And then the other one will be at 500 minus. Notice that I drew them here on my phase plane portrait with the larger one above the smaller one, the plus above the minus one here. And if you think about the signs on the differential equation, when p is bigger or between or smaller than these equilibrium solutions, you'll see that you end up with a phase plane portrait that looks like that. You've got decreasing, increasing, and then decreasing. So you've got a stable equilibrium solution here at this value, and depending on h, here I'm looking at a lot of different constant values of h, but all of the constant values of h that would be less than 10 will give us this situation. And so I'll have one stable equilibrium solution here and then an unstable equilibrium solution here. Again, if the population starts out near where it was before we introduced harvesting, started out at 1,000, what this model shows is it should restabilize at this new lower level, something less than 1,000, but a stable equilibrium. If the population dipped below this level, this model shows that that population would die out. All right, and then one more situation left to consider. So we've got our bifurcation value at h equals 10. We've considered h less than 10, and then the other situation to consider would be what happens when h is greater than 10. So when h is greater than 10, you end up with a negative inside this radical for your equilibrium solutions, which means you have non-real equilibrium solutions. So in the context of the problem, there are no real equilibrium solutions. So for all real values of population, which are the only ones that really make sense in the context of the problem, you end up with a phase plane portrait where the solution curves are always decreasing, which means they're going to look like this, which means the population is going to die out. So what this model shows is that as long as the wildlife manager chooses a harvesting level that is less than 10, then the population will stabilize at some value less than it was originally stabilized at this new value here. So depending on what the level of h is, you can calculate what this model shows that is. You'd want to be very careful about choosing anything that's close to 10. Remember, with models, there's always some estimation. These constants that were in our original equation are probably based on estimates. And so there's always some margin of error on those estimates. So you want to be very careful about choosing any h level that is close to 10, close to this bifurcation value, because you end up with this completely different behavior on either side of that level. And there could be error in these estimation of these constants. And so you want to make sure that you're safely away from that bifurcation value when you choose that harvesting level. All right, so there are some problems in your homework like this where they describe different sorts of population models to start with and different sorts of changes to that. This is one where we started harvesting or removing individuals from the population. There could be a model where you have immigration, where more parts of the population come into, and so that would be adding a level. You could be, instead of adding or subtracting a constant amount, it could be some amount that is proportional to the population. And so the main thing that you want to think about here is not necessarily this exact problem, but being able to take these population models that you already have studied and then thinking about how to modify them to reflect this new behavior. And then often that new behavior might involve some sort of constant that is unknown. And so then examining that, you want to look for that bifurcation value where the nature of your solution is going to change. And so sometimes that requires doing a little bit of algebra. Notice that I really couldn't tell what that bifurcation value was going to be until I did a little bit of algebra and some simplifying. But once I got it in this form, it's pretty obvious that this quantity inside the radical here is going to be what's going to control the kinds of equilibrium solutions I'm going to get and what's going to happen with the population. All right, so try some of those in your homework. Remember, you can always ask questions if you get stuck.